a question. Not question.
They just go on the cabinet. All right, so continuing to look at graphs of trig functions. We'll look at some questions today on when you're given an equation, when you're given the graph, what is the equation? So this one says write the equation of that function in the form y equals a sine b x minus c plus d, where a is greater than 0, which means that this graph, you could not write the equation with a negative value of a, meaning that the graph is reflected over the x-axis. It says a has to be greater than 0. So we need to determine what the 4 parameters are. No, she can't.
I could have put them on my laptop.
Okay, so we need to find those 4 parameters, A, B, C, and D. And I think the easiest thing to do is to start with our D value, because D tells us where the horizontal midline is. The horizontal midline tells us what the value of D is, and it's halfway between the max and the min. This graphs have a maximum of 4 and a minimum of 0. Halfway between that is 2. That's the horizontal midline. That is our D value. Okay, because it is the horizontal midline. Right, we can also talk about the fact that that is the vertical displacement. Right, the graph has been shifted up 2 units. So once you have that, then I think it's quite easy to see what A is. The amplitude, A, is the distance from that horizontal midline to the max or down to the min. And it's 2 units away. The maximum is 2 units above that line. The minimum is 2 units below that line. So that is our A value. 2. It is our amplitude. B controls the horizontal stretch. And to figure out what B is, we need to know what our period is. So we can count that on the graph. Remember, the period is how long it takes to go through one cycle. So you can take any point on the graph and see how long it takes to get to that same point. It can be from a maximum to a maximum, a minimum to a minimum. Horizontal midline going upwards to the horizontal midline going upwards, it doesn't matter. Probably the easiest thing to do would be to look at this minimum to that minimum. That shows a period of 2 pi on 3. So our period is 2 pi on 3. And so there's a couple different ways that we could get our B value from this. Right? We've talked about an equation that we use to find out our new period. Our period is 2 pi divided by B. That formula is not on the formula sheet, but it's something that we can use if you remember it. The period can be found by going 2 pi over B. So if you compare these two statements, B has to equal 3. Now here's another way you can get your B value of 3. For most sine and cosine graphs, the period is 2 pi radians. This one, the period is 2 pi on 3. It's 1/3 of 2 pi. So that means that the graph has been horizontally stretched by a factor of 1/3. And remember, the stretch factor and the B value are reciprocals of each other. So horizontal stretch of 1/3 means also that B equals 3. The last thing we need to do is get our C value. And C is our phase shift, right? Has the graph shifted left or right? And because we're graphing or writing the equation of a sine function here, sine always starts in the middle, heading upwards. So on this graph, that would be right there. It is 1 unit to the right of the y-axis. And the scale here on this grid is pi on 6. Between 0 and pi on 3, that's been divided up into 2 equal sections. This first line is that dividing line between those two sections. So each of these sections is half of pi on 3. Pi on 3 times a half is pi on 6. So our C value is positive pi on 6 because we have a phase shift here of pi on 6 to the right. So C is pi on 6. So now we can write our entire equation. Y equals A is 2 sine. Our B value is 3, bracket. The value of C is positive pi on 6. Remember the general equation is x minus C. So when you put a positive value in for C, it stays x minus. And our D value is plus 2. So there's that equation. Part B says, what if it is a cosine function where A is positive? The only thing that'll change if it's a cosine function is the phase shift. The amplitude is the same, the period is the same, your vertical displacement is the same. The only thing that changes will be the phase shift. And you have to remember that cosine starts at the maximum. And so in this case here, it could either be at this point there or that point there. They are the same distance away from the y-axis. Normally when we write our equations, it's with the minimal possible phase shift. And on the diploma exam, they'll actually use that language, minimum possible phase shift. But in this case, it wouldn't matter. Those two maximum points are equidistant from the y-axis. So if it's a cosine function, we would say y equals 2 cos 3 bracket. It could be x plus or minus pi on 3. Either one of them are correct. Because it could be this point here where C is positive pi on 3. So that means it's x minus pi on 3. Or it could be this point here where C is negative pi on 3, which would give you your x plus pi on 3. They are the same distance away from the y-axis. So either one will work. Then it says you can use your calculator to verify our solutions. Whoops. So we'll put our two equations in there. 2 sine 3, open another bracket for x minus, and I'll have to open another bracket for pi on 6. So close the bracket on the pi on 6, close the bracket on the x minus pi on 6, and close the bracket on the 3 bracket x minus pi on 6. And then we have plus 2 on the end. Our second equation is 2 cosine 3. Open a bracket, and we can put x minus and another bracket for pi on 3. Or 2 cosine 3 bracket x plus pi on 3. With the plus 2 on the end. Now before we can hit graph, we've got to adjust our windows as well. If I use the same scale as what's on this grid, which we should, we also have to be in radian mode because those values are in radians. So for my windows, I'm going to go from negative 2 pi on 3 on the x-axis up to positive 7 pi on 3, right? This is 5 pi on 3. Another one would be 6 pi on 3, which is 2 pi. Another one would be 7 pi on 3. And when you hit enter, your calculator does convert that into a decimal. That's fine. My scale here is pi on 6. And for y, I'll go from negative 2 up to positive 5 and a scale of 1. So now when I hit graph, a couple things are going to happen. You're going to see all three graphs drawn really quickly. They should all be drawn on top of each other, which means that those equations all represent the same graph. And then we'll use our calculator to pick out some points to make sure that the points line up the way they should. So when I hit graph, it's going to happen really fast. It'll graph all three, one over the other. And then, like I said, if we go into the trace mode and we put in some values for x, for example, when x is 0, that's the origin point, 0, 0, that point checks out. When x is pi on 3, we should be at positive 4. So let's put pi on 3 in. So that checks out. And let's check this point right here. Let's check that point right there. So remember that our scale is pi on 6. So the first line is 1 pi on 6, 2 pi on 6, which reduces to pi on 3. Then we're going to be at 3 pi on 6, which is the same as pi on 2. When x is pi on 2, well, my y value should be positive 2. So trace, I'll let x equal pi on 2. And I get the right y value, positive 2. So I just checked 3 points from my calculator from the 3 equations that I came up with. They match the points on the graph, so we can be certain that our equations are correct. So you should never get these wrong because you can always check them against what the graph looks like. All right, so we'll do the same thing for this one. Write the equation as a sine function where a is positive and then a cosine function where a is also positive. Like we did before, I'm going to start with the horizontal midline, our vertical displacement. This graph has a maximum of 1 and a minimum of negative 3. So the middle would be halfway between them. Those two, the max and min, are 4 units apart. So the middle will be halfway in between or 2 units apart. 2 units below the max or 2 units above the minimum. That also gives us our d value, right? Our vertical displacement is down 1, so therefore d is negative 1. Our d line is halfway between the max and the min, and the distance from the d line up to the max or down to the minimum is the amplitude. Our amplitude in this case, again, is positive 2. So that is our a value, positive 2. The maximum is 2 units above the middle. The minimum is 2 units below the middle. All right, now we got to find our period so we can see if we have a b value. So let's go from, let's say, this maximum point to that maximum point. Once again, the scale here is pi on 6 because between 0 and pi on 3, it's divided up into 2 equal sections. So each section will be half of a pi on 3, which is pi on 6. So if I start from this maximum point to that maximum and I count how many pi on 6s I need to travel, it's 1, 2, 3, 4 pi on 6s, which is 2 pi on 3. That is our period. And if you compare that to 2 pi over b, once again, b has to equal 3. The other way you can look at it, you can use logic. Normally the graph of sine and cos has a period of 2 pi. This one is 2 pi on 3. It's 1/3 of 2 pi. So the graph has been horizontally stretched by a factor of a third. The b value and the horizontal stretch factor are always reciprocals of each other. So either way, b equals 3. And then finally, for a sine function, remember that the sine graph starts in the middle heading upwards. And the closest point to the y-axis where that occurs can actually be this point over here. Let me change a different color here. This point over here, or that point over there. The graph of sine goes upwards through the horizontal middle. That's where it starts. Those 2 points are the same distance away from the y-axis. They're both pi on 3 away. So for a sine function, c can equal either plus or minus pi on 3. And so our equation will be y equals 2 sine 3 bracket x plus or minus pi on 3 minus 1. Part B says, what if it is a cosine function? The only thing that'll change is our c value. Everything else stays the same. So if it's a cosine function, we're looking for the closest maximum point, which is right there. It is 1 unit to the left, so c is negative pi on 6. And the equation would be y equals 2 cosine 3 bracket x plus pi on 6 minus 1. So again, you can check those. So I have 2 sine. Actually, what happens if I just change that to cosine? Okay, that's good. So, because there's only one equation with cosine, there's 2 equations with sine that we could try. And the only difference here is that it's going to be plus pi on 6, and then the d value is minus 1. Minus 1. So there's the cosine equation. Our first sine equation is 2 sine 3 bracket x minus pi on 3 will work. I just have to change my d value to minus 1. And then for the last one, again, change that to a sine. And then I have x plus pi on 3, and the d value again is minus 1. I don't know if I probably have to change the windows. It does go from negative pi on 3, looks like to 2 pi on 3, 3 to 4 pi on 3. And I'll keep my scale at pi on 6. For my y minimum, I should go from negative 4 up to positive 2 on the y-axis. So those definitely have to be changed. So once again, all 3 equations are drawn, one over top the other. So that tells us that all 3 equations that we came up with are the same, give us the same graph, I should say. And just to check to make sure we have the right graph, if we check this first minimum point here, when x is pi on 6, y should equal negative 3. So go into trace and let x equal pi over 6. We get the right y value, negative 3. At pi on 3, we should be at the horizontal midline where the y value is negative 1. So if I let x equal pi on 3, y should equal negative 1, and it does. And the last point I'll check this one point here, this first maximum to the left of the y-axis. That's when x is negative pi on 6, y should be positive 1. And it is. You never get these wrong because you can always check them in your calculator to make sure. All right. We've talked about the fact that there are some natural phenomena that occur in the world where the data follows a sinusoidal pattern. One of them is the height of the ocean due to the changing tides. So Prince Rupert, BC has the deepest natural harbor in North America. The depth d in meters of the bursts for the ships can be approximated by this equation. 8 cos pi on 6t plus 12, where t is the time in hours after the first high tide. First thing we're asked to do is to graph the function for 2 cycles. So this is a cosine function. It starts at the maximum. And in this case, there is no phase shift. There is no c value in this equation, which means the graph is not shifted left or right. So you got an amplitude of 8, and you have a vertical displacement of plus 12. Remember, our d value tells us our vertical displacement. It tells us where our horizontal midline is. It is at plus 12. So let's start by drawing that there. And because the amplitude is 8, this graph is going to start 8 units above the horizontal midline. 8 units above 12 is at plus 20. So that's where this graph is going to start, plus 20. And it'll be back at that same height after one complete cycle of the graph, or after the graph goes through one period. So let's find out what the period is by going to pi divided by b. Our b value here is pi on 6. So dividing by pi on 6 is the same as multiplying by the reciprocal, 6 over pi. The pi's cancel, and you'll get 12. Now we're going to see that the actual period for the change in tides is approximately 12, but it's not actually exactly 12 hours. But it's approximately 12 hours. But again, we're going to see that as we look at some other examples later on. We're going to come across an equation where it's a little more accurate for the actual change in tides. So according to this equation, though, our period is 12. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, there's the end of our first cycle after 12 units, or in this case, 12 hours. And another 12 hours, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, takes us right to the end. There's the end of the second cycle. Halfway in between the first maximum and the next maximum, you're going to be at the minimum, or 6 units from where you start. You'll be at the minimum. And the minimum will be 8 units below the middle. The middle's at 12. If you go 8 units below that, you'll be at positive 4. So at 6 units in, 1, 2, 3, 4, 5, 6, we're at the minimum, which is positive 4. And 6 units from the next maximum, you'll be at that same minimum value of positive 4. 1, 2, 3, 4, 5, 6. Right? That's halfway between those two maximums. And halfway between the max and the min, you'll be in the middle. So 3 units. 1, 2, 3, you're in the middle. After the minimum, 1, 2, 3, you're in the middle. After the next max, 1, 2, 3, you're in the middle. 1, 2, 3, you're at the minimum. 1, 2, 3, back to the middle. So this gives us all of our critical points with which to draw our graph and it's hard for me to draw, a good sketch here, but I'll tell you one thing, and that is that if you have a question where you have to draw a sinusoidal curve on a diploma exam, you have to make sure that the graph has contour to it. There can't be a series of V's or straight lines. You'll lose a mark for that. The graph of a sinusoidal function has curve to it. Okay, so this top part has to have a curve, the bottom part has to have a curve. So they've got to have curvature to be correct. So there's our graph for 2 cycles. We've already answered part B, which was what was the period. We needed that to draw our graph, so we already figured that part out. Now part C, an ocean liner requires 13 meters of water to dock safely. From the graph, determine the number of hours per cycle the ocean liner can safely dock. So the easiest way to do this would be to use the graphing calculator. So we'll clear the three equations that we have in there. We'll put this equation in, which is 8 cosine. I'm going to have pi over 6 times t. Well, we can only use x as a variable. And it's pi over 6 times x over 1. So we can go x times pi over 6. Or pi times x over 6. It doesn't matter. And then you have the plus 12 on the end. So there that equation is in there. Now, we're still going to be in radian mode. The only time you're switching into degrees if you're actually told that your x-axis is in degrees, right? And definitely it's not here. We stay in radians. But we will have to change our window, and I mean the graph on the page tells us what our window should be. I'm going to go from -2 up to +26 on the x-axis. The reason I'm starting at -2 is just so we can clearly see where the y-axis is. And I'll put my scale at, let's say, 3. For my y values, I'm going to go from, let's say, +2 up to +22. And let's use a scale of 2 on the y-axis. So now when we hit graph, we should see the graph, which we do. And we are told that the depth of the water must be a minimum of 13 meters for the ocean liner to safely dock. So what I'm going to do now is I'm going to put a second equation in. In y2, I'm going to type in 13. And when I hit graph, it'll draw the line y equals 13. And from the start of the first cycle, where the tide is actually at its highest point, till it gets to that first point of intersection, the ocean liner can dock safely. In this portion of the graph, it can dock safely. So we need to find out what this point of intersection is by going second function trace, number 5 for intersect, enter, enter, and I'll put my guess at 2. And it's actually 2.76. So for 2.76 hours from the start of that high tide, the ocean liner can dock safely. So this is part C. The first section is 2.76 hours. And then the next section will be from this point of intersection, where it comes up and hits that line y equals 13 again, up to the maximum, which is at 12 hours. Okay? So we got to find this point of intersection now. Second function trace, number 5 for intersect, enter, enter. I'll put my guess at 5. No, didn't put it high enough. Try again. Let's try our guess at 8. There we go. It's actually 9.24 hours. So between 9.24 hours and 12 hours, again, it asks us to talk about how many hours per cycle. So we can only go to the end of the first cycle. So again, from 9.24 hours to 12 hours, or we can go 12 hours, take away 9.24 hours, which actually is also 2.76, I think. So 12 minus 9.24 is also 2.76. No, because the graph is symmetrical. So it's not coincidence. But it doesn't mean it's always going to work out that way. It all depends on what the line is that you're also comparing it to. So that is 5.52 hours. And you can convert that into hours and minutes if you want. So that 0.52 of an hour is 0.52 times 60 minutes. 0.52 times 60, so approximately 31 minutes. So 5 hours, 31 minutes is how much time per cycle the ocean liner can safely dock. That doesn't mean it can stay there the whole time, because after that 2.7, between 2.76 and 9.24 hours, the water is not going to be deep enough for that boat to stay in there. So it's going to have to get out. So part D says, if the minimum depth of the berth occurs at 6 hours, determine the depth of the water. So that's 4 meters. We already calculated that. At what other times will the water level be at a minimum? Well, it'll be every 12 hours, because that's our period. Okay, so for part D, 4 meters every 12 hours, because according to the formula, that is the period of this equation. Okay, so here's another equation, or another example, at a different place along the west coast. The depth D in meters of the water in harbor at New Westminster, BC, is approximated by that equation. So completely different equation. Remember, it said that Prince Rupert had the deepest natural harbor in all of North America. So the vertical displacement was a larger number, the amplitude was a larger number as well. But once again, we want to graph this for 2 cycles starting at time equals 0. Once again, this is a cosine function, so cosine starts at the maximum, and there is no C value here, so once again, there is no phase shift. This graph will start on the y-axis, and it'll start at the y-axis 0.6 units above 3.7. Our D value is 3.7, so that will be where our horizontal midline is. So this is 2, 1, 2, 3, 4. Between 2 and 4, there are 4 units there, so halfway would be 3. So each unit counts for half of a meter. So this is 3, that'll be 3.5, 3.7 will be just above 3.5. So there's our horizontal midline. That is at y equals 3.5. Sorry, 3.7, not 3.5, 3.7. Okay, and our maximum, because our amplitude is 0.6, our maximum will be 0.6 above the middle. You can find your maximum by taking the D value and adding the A value. 3.7 plus 0.6 is 4.3. So 4.3, so that's 4. 4.5 would be right there. 4.3 is just above it. Or, I'm sorry, just below 4.5. And we'll be at that same height after one complete cycle is done. Our period is found by going 2 pi over 1 divided by our B value, which in this case is 2 pi over 13. And to divide by a fraction, we multiply by the reciprocal. The 2 pi's cancel, and you're just left with 13. So the last equation said the period was 12 hours. This equation says the period is 13 hours. Again, A little bit later, we'll see an example where it's going to be a little more accurate. It's going to be between 12 and 13 hours. But this tells us that at 13 hours, we'll be done our first cycle, and we'll be at the same height that we started at. And then at 26 hours, another 13 hours, we're back there. So halfway between these first two maximum points, you'll be at the minimum. Our minimum can be found by going d minus a. The horizontal midline, subtract the amplitude. So that would be 3.7 minus 0.6, which is 3.1. That's the minimum. So halfway between the first two maximums, they are 13 units apart. So at 6.5 units, we'll be at 3.1. 1, 2, 3, 4, 5, 6.5 is approximately right there. 3.1. And then halfway between the next two maximums, or another 6.5 units, we'll be back to the minimum. 1, 2, 3, 4, 5, 6.5. Halfway between those two, halfway between 0 and 6.5 would be 3.25. That's what will be in the middle. 1, 2, 3.25 in the middle. Halfway between the next two, the next minimum and maximum, we'll be back to the middle. So 1, 2, 3.25. 1, 2, 3.25. 1, 2, 3.25. So the graph looks something like that. And we can check. We can check our graph by putting this equation into the calculator. 0.6 times the cosine. It'll be 2 pi x over 13. 2 pi x over 13 plus 3.7. For our windows, I can go from -2 to, let's say, 27 on the x-axis. I'll keep my scale at 3. For y, I'll go from 2 till 6 and keep my scale at 1. So when I graph it, it should look the same as what's there. I can check, for example, at 13 hours, I should be at my maximum value. And the maximum value was 4.3 at 13 hours. So trace 13, enter. Yep, I'm at 4.3. 3.25 hours past that, I should be at the middle value. I should be in the horizontal midline, which is at 3.7. So 3.25 hours would be 16.25. I'm at my 3.7. Okay, so certainly appears like my graph is correct. So part B, we've already answered that. We found our period to do our graph. In this case, the boat requires a minimum of 3.5 meters of water to launch safely. How many hours per cycle can the boat safely launch? So again, we'll go to our calculator, we'll do a second equation, y equals 3.5. And so like we did before, we'll find that first point of intersection. I'll put my first guess at 2 hours, and it's actually at 3.95 hours. So this is part C. 3.95 hours plus. And like before, we got to go from our second point of intersection up to this point here, which happens at 13 hours. So between this time and 13 hours, we got to find our second point of intersection. Second function trace, number 5 for intersect, enter. I'll put my guess at 8 hours, and it's actually at 9.05 hours. So between 9.05 and 13 hours. Which again is 3.95. So again, it's not a coincidence there, but it's only in this case also because this graph starts at the maximum. If this graph had been shifted over a little bit, then we probably wouldn't be getting those same two numbers. So you always got to use your calculator to make sure. So 7.9 hours, or 7 hours and 0.9 of an hour. So 0.9 times 60 minutes is 54. Yeah. So 7 hours, 54 minutes is how long per cycle that boat has to safely go into the harbor. What is the depth of water at 7 hours? Well, we can use our graphing calculator for that. Go into the trace mode and let x equal 7. We can see it's at a depth of 3.12 meters. This one was in meters, right? Yeah. At what other times is the level at this depth? Well, it will be there every 13 hours. Because that is the period. The period is 13 hours, so every 13 hours it'll be in the same spot. Okay, so we're going to skip forward here. This is page 45. So we've said that a function whose graph resembles a sine or cosine curve is called a sinusoidal function. The graph of a sinusoidal function is called a sinusoidal graph. Once again, many periodic phenomena have sinusoidal graphs, including the time of sunrise as a function of the day of the year. So if you wrote a table with days 1 to 365, and you copy down the time of sunrise on every day, and you graph that data, it would follow a sinusoidal curve. Same thing with the time of sunset. It would do the same. The height of a chair of a Ferris wheel as a function of time. As a Ferris wheel goes around, the height of the wheel will change. It'll increase and it'll decrease. It'll increase and it'll decrease. It'll follow a sinusoidal pattern. The depth of the ocean due to changing tides, we've already seen that one. Okay, so we'll do some more work working with equations. Most of the equations will be functions of time and the variable used will be t. The period of the graph will be in time units. And graphical methods will be used to solve problems, and determining a suitable window is an essential feature of the solution. So the depth d meters of water in a harbor t hours after midnight can be approximated by this equation between 0 and 24 hours. Determine the max and min depths. So we just saw that you can find the max and the minimum by using that formula, those formulas involving D and A. The minimum can be found by going D minus A. So in this case here, and before we do this, let's go back and look at the equation. Normally we would write it in the form where the D value is at the end. For some reason, the way they wrote this equation, the D value is the first number, but we can move it to the end. That'll be 5 times the cosine of 0.5t plus 12 at the end. That's how we're used to seeing our equations written. So our D value is 12 minus our A value of 5. So that gives us a minimum of 7 meters. And our maximum can be found by going D plus A. The horizontal midline value plus the amplitude will take you up to the high point, which is 17 meters. The period of the graph, well, period is always 2 pi divided by b. And in this case here, our b value is a half. So if we go 2 pi divided by a half, which is the same as multiplying by 2, or 4 pi, 2 pi times 2 is 4 pi. This is a more accurate number for the period of the changing tides. 12.6 hours approximate. Remember I said it's between 12 and 13. This is a much more accurate estimation for the period for the changing tides. So based on these first two questions, we get a really good idea of what our windows should be. Now, if you're asked to write the windows, you express them in square brackets, and there's three things that you write. You write the min, comma, followed by the max, comma, followed by the scale that you would use in your calculator. And there really is no, well, there are right and wrong answers, but as long as, if you're finding a point of intersection between two graphs, as long as your point of intersection falls within the min and the max, that's what you need to make sure happens. So in this case here, though, for our x values, so we always do our x1 first, that's what the period tells us. Our period is 12.6 hours. So maybe I go from -1 up to 13 hours. That will show one complete cycle of the graph, right? That is actually a distance of 14 hours. Our period is only 12.6 hours. So that'll work. And our scale can be really any number. It can be 1, it can be 2, it can be 3. You probably wouldn't want to have it a number greater than the spread between the min and the max. That wouldn't make any sense, but I chose a scale of 2. Now for our y, that's where our min and max values come in to play. We found our minimum was 7, our maximum was 17, so maybe we'll go from 6 to 18. And a scale of 2 once again. Then it says, or asks us, what is the depth of water to the nearest tenth of a meter at 2 a.m. or 2 hours after midnight? So we could do this a couple different ways. We could graph the equation in our calculator. That's certainly one way to do it. So I'll go y equals, clear that out, I'll go 5 cos 0.5x, close the bracket, plus 12 at the end. My windows, I went from -1 to 13 on the x-axis with a scale of 2. I went from 6 to 18 on the y-axis, also a scale of 2. So now when I hit graph, I can simply go trace and let x equal 2. That's 2 hours after midnight. And you can see the depth of the water is 14.7 meters. right from the calculator. But another way we can do it, we'll still use our calculator, but we can just use the equation. We can let t equal 2 in the equation. So it'll be cosine of 0.5 t times t, and in this case t is 2, plus 12. I forgot the 5 in front of the cosine. So our calculator is in radian mode, which is what we need. We can just go 5 times the cosine of 0.5 times 2, which will actually be 1. So we could have just put the 1 in there. And then you have your plus 12 at the end. You get exactly the same answer, 14.7. Right? So you can use the graph, or you can just use the equation. The graph comes from the equation, so you're really doing the same thing. Part E, a ship requires a minimum of 8.5 meters of water in harbor. Sorry, a ship which requires a minimum of 8.5 meters of water is in harbor at midnight. By what time to the nearest minute must it leave to prevent grounding? So we needed the graph for that one. We'll put a second equation in 8.5. So it has to get out before that first point of intersection. So to find out what that is, second function trace, number 5 for intersect. Enter. I'll put my guess at 5. It's actually 4.69 hours after midnight, or 4 hours and 0.69 of an hour, or 0.69 of 60 minutes. So because this number is in my x value, if I just go quit and now I go x times 60, whoops, that's not right. I got to go x minus 1 times 60, or minus 4, excuse me. I got to take the 4 away. So I just have the decimal. Yeah, times 60 minutes. So 4 hours, 42 minutes. And when can it safely return to the harbor? So that'll be the second point of intersection, second function trace, number 5 for intersect, enter. Let's put my guess here at 7. And it's actually 7.87 hours. Or 7 hours and 0.87 of an hour. So again, if I take my x value and I subtract the 7 hours, that'll just leave me with my 0.87 that I multiply by 60. So 7 hours, 52 minutes is when it can safely return to the harbor. In a certain Alberta town, time of sunrise for any day can be found using this formula. So I would probably rewrite it just a little bit different, so it's in the form that we're used to dealing with. And that is that if we look at what's happening inside those big rounded brackets, you've got 2 pi, it's being multiplied by d minus 78 and then divided by 365. So we can put the 2 pi over 365 and then d minus 78. That's the same thing. That's just the format that we're used to seeing it in. So write a suitable window. So we need to know what our period is. And if you look at the b value, 2 pi over 365, Our period is 2 pi over 1 divided by our b value of 2 pi over 365. When you multiply by the reciprocal, the 2 pi's are going to cancel, and you're just going to have 365, which makes perfect sense. That's how many days there are in a year. And we also need to know what our max and min values are. Our minimum is d minus a. 6.3 minus 1.79. Our amplitude is 1.79. The negative in front tells us that the graph was reflected over the x-axis. The amplitude is the absolute value of a. So 6.3 minus 1.79 will give us our minimum value. So 4.51, that's our minimum, and our maximum will be d plus a. 6.3 plus 1.79. 8.09. So these are all things that we need to write our windows. So I'll do them down here. So for our x, we can go, let's say, from negative 10 up to 370. And maybe a scale of, I don't know, 50. For our y windows, we can go from 4 up to 9 and a scale of 1. Now part B says use the formula to determine to the nearest minute when the sun rose on May 7th, which was the 127th day of the year. So that's where D is 127th. So T would be negative 1.79 times the sine of 2 pi over 365 times 127 minus 78 plus 6.3. So you might find it easier here to work inside the brackets first. So 127 minus 78. You're going to multiply that by 2 pi and divide by 360. 365, I should say. So inside the big square brackets, you work all that out. It's 0.843, etc. That's what you need to take the sine of. So I'll go negative 1.79 times the sine of the previous answer, close the bracket, and then plus 6.3 at the end. So 4.96 hours is when the sun will rise on May 7th. 4.96 hours. So that's almost 5 a.m. 4 hours, and I'll subtract 4 from that number. Just gives me the decimal. Multiply that by 60. So 4 hours, 58 minutes. 4:58. 4:58 a.m. So you can use the formula for that, or you could use the graph, which we're going to need for the next part anyways. Yes?
It was like 16.
16. Where are you getting 16 from?
Well, actually, the value for the hours is like 16.
Would it be what?
Would it be like PM, before PM?
The only way it would be 4 p.m., it'd have to be after 12 hours. Oh, so you're saying if it's 16 hours? So yes, that would be in the afternoon. Yep. Yep. Okay, so again, for question C, we're going to need the equation in our calculator. We're going to have to graph it. So negative 1.79. Well, I forgot to write the sign there when I wrote it with the 2 pi on 365 out in front. So put that in there now. And so I'll have to open another bracket for my b value of 2 pi over 365. So close the bracket on our b value, open another bracket for x minus 78. Close the bracket on that, and then close the bracket on that open when I hit sign. And then plus 6.3. So our windows, we have them down below there. We're going from negative 10 up to positive 370, and a scale of 50 on the x-axis. From y, we went from 4 up to 9, and a scale of 1. And I need to put a second equation in there, y equals 7. We want to know on what days of the year the sun rose at 7 a.m. So y equals 7 will be our second equation. So we need to find those 2 points of intersection. So it's close to day 50 because that was my scale. Actually, day 55. As well as, so that's 50, 100, 150, 200, should be close to day 250, 280, 284. Right? Okay, so there's an assignment there you can work on. There's 2 pages. I will post the solutions to Google Classroom so that you can check your answers. Okay?